Hi, in this lectures, we are going to study the most important concepts in solid mechanics, namely normal and shear stress. To start, let me use the example that we saw in the last lectures. If you remember, after sectioning through the structures, with the knowledge we learned in statics, we are only able to find the resultant internal force and moment acting on this whole surface. A problem with this resultant is they do not tell us the internal force at a specific location and whether the body is strong enough to withstand the external loads. To answer such question, engineers came up with the concept of stress, which is defined as the internal force acting at each location on a differential area like this one. It should be noted that while the area dA here is plotted big enough so that you can visualize, it should be understood as the differential area whose value approach to zero. Having said that, the stress can be defined by this limit formula. Having understood its definition, we will now discuss about different types of stress. In engineering mechanics, we usually decompose the stress into two components. One perpendicular to the section plane, which is called normal stress, and the other in the section plane, which is called shear stress. As you can realize, the normal stress indicates whether the material is under tension or compression. The shear stress indicates the sliding effect. Now, it should be clear to us that the stress is determined for each point within a body given the orientation of the section plane. So suppose we have a bar axially loaded at the centroid of each end like this. If we want to ask someone the stress at a point P, we should first define the orientation of the section plane. For example, if we define the plane perpendicular to the longitudinal axis of the bar like this, there will be only normal component of stress at point P. However, if we use a different plane like this one, there will be both normal and shear component of the stress at point P. So whenever you talk about the stress at a point within the body, you should ask yourself the following question. On what direction or plane would you like to observe the stress? Now let us talk about the unit of stress. As you may already realize from the definition of stress, its units are similar to those of pressure. In international standard system, its typical units are Pascal, kilopascal, megapascal, or gigapascal. In US customary system, stress are usually measured in PSI, which stand for pound per square inch, or KSI, which is kilopound per square inch. Please note that this is not an exhaustive list, so you might see something like kilonewton per square centimeters or kilopound per square foot. Let us determine the stress for the most basic scenario that I showed before when a bar is subjected to external point loads at the centroids of its two ends. And we need to find the average normal stress on the cross-section of the bar. First, to make it simple, we will assume that the bar is made with a homogeneous and isotropic materials, meaning it has the same physical and mechanical properties throughout its volume, and the same properties in all directions. Now, to find the average normal stress, we will first section through the bar using a plane perpendicular to its longitudinal axis. Then we will plot the free body diagram for either half of the bar and use it to find the internal loadings at the section location. As you can see, for axially loaded bar, such resultant internal loadings contain only normal force component N, which is equal to the external force P. Now, suppose the normal force N is distributed evenly over the section area. We can easily find the average normal stress using this equation. Now, in order to help you better visualize the stress in the above example, let us consider a small volume element at the cut location with the top and bottom surface oriented perpendicular to the longitudinal axis of the bar. Based on the previous slide, we know that there exists only normal stress at the top and bottom surface of the element. Then, if we plot the free body diagram for this element and use the equilibrium of forces in the vertical direction, we will be able to see that the normal stress are the same at the top and bottom surface of the volume element. It is important to note that under this condition, the material is said to be subjected to uniaxial stress. As you can see, for uniaxial stress, the materials can be subjected to either tension or compression. In the case of tension, the normal stress is called tensile stress. And in the case of compression, it is called compressive stress. Next, we are going to see how we can determine the average shear stress for a loading scenario shown on the screen. In this scenario, we have a force F acting at the middle of the bar. As you can see, when we increase the magnitude of the force F, the bar may deform and fail by sliding at these two surfaces. So let us section through these two locations and plot the free body diagram for the middle section of the bar. Based on the equilibrium of the segment, we can determine the resultant internal shear force on each of these surfaces, V, to be equal to F over 2. Then, if we assume a uniform distribution of shear stress, we can calculate its average value using the following equation. As you will see later on, the shear stress predicted by this equation is much smaller than those obtained with a more precise investigation. However, engineering codes still allow it to be used for determining the size or cross-section of small elements like bolts, or for obtaining the bonding strength of glue joints subjected to shear loadings. Now let us try to understand a very important property of shear stress, which is called complementary property. For that, consider the block on the screen, which has been sectioned and is subjected to the internal shear force V. Let us extract this volume element, zoom in and name the shear stress on each surface. As a convention, we use two subscript letters for naming the shear stress. Like you can see here, the first letter is to indicate the direction of the plane, which contains the shear stress. And the second letter is to indicate the direction of the stress itself. With such naming, we can plot the free body diagram for the element to study the relationship between those shear stresses. For example, by studying the equilibrium of force in y direction, we can understand the relationship between the shear stress on the top and bottom surface. They are equal to each other but act in opposite direction. Or by studying the equilibrium of moment about x-axis, we can see the relationship between the shear stress on two neighboring surfaces. The relationship can be summarized in this figure. We describe the complementary property of shear. This property is very important and we will use it later on to explain the relationship between the longitudinal and transverse shear in members subjected to twisting or bending. Now let us take a look at some example on calculating normal and shear stress. In this first example, we are given a bar with a constant cross-section and a loading description. We are asked to determine the maximum average normal stress. Let us first try to understand the question. Why we know what average normal stress is. I suppose some of you might get confused by the word maximum here. As you can see, since the bar consists of three different segments, what that means is we need to determine the average normal stress for each segment and then find the maximum value among them. As to the first task, we already know that we need to find the resultant internal normal force in each segment. Of course, for that we should use the method of section. For example, to find the normal force within segment AB, we should cut through segment AB and then plot the free body diagram for either the left or the right segment of the entire bar. Then, based on the force equilibrium, we can find the resultant internal normal force in segment AB to be 12 kN. We do the same for segment BC and segment CD. Then we can plot something called normal force diagram, which is similar to the shear and moment diagram that we learned in statics. But this diagram indicates the normal force for the entire bar in each segment. With the diagram, we can see that the segment BC is subjected to the largest internal normal force. Since the cross-section of the bar is constant, the maximum average normal stress will be in segment BC. So to answer the question, we just need to find the average normal stress in segment BC. Since we know the dimension of the cross-section area of the bar, we can find the average normal stress in segment BC using the equation that we discussed earlier in these lectures. Now, here is a visualization of distribution of normal stress in any arbitrary cross-section of segment BC. Next, we are going to study an example of shear stress. As you can see, in this example, we have a beam supported by two pin supports at the two ends. With the dimension being provided and the load description, we are asked to determine the average shear stress in the pin at A and the pin at B. So let us analyze the problem. First, we know the forces exerted by the beam onto the pin at A and at B can be found by studying the equilibrium of the beam. The reason is, according to the third Newton law, the force exerted by the beam onto a pin is equal to the force exerted by the pin onto the beam, but in the opposite direction. Second, we notice the difference between the pin at A and the pin at B. Specifically, while the pin at A is supported by double shear forces on two surfaces, the one at B is supported by a single shear force on one surface only. So we should take that into account later on. For now, as being discussed, let us plot the free body diagram for the beam to find the support reaction at pin A and pin B. As you can see, if we start with sum of the force in x or y direction for this free body diagram, we will end up having two unknowns in the equilibrium equation. On the other hand, if we take sum of the moment about point A, we will be able to find the force FB right away. That is the reason why we should start with the sum of the moment about point A in this solution. Then, based on sum of the force in x and y direction, we can find the force AX, AY. With AX and AY components, we can then determine the resultant force acting on pin A using Pythagorean equation. Then, as we mentioned earlier, since the pin at A is subjected to double shear surface, the shear force at pin A will be equal to a half of support reaction FA. Please be careful, that is not the case for pin B, which is subjected to a single shear surface. Because of that, the shear force at pin B is equal to the support reaction FB. Now, with the cross-sectional area of the two pins known, we can easily find the average shear stress for each of them using the equation we discussed earlier in these lectures. That concludes my presentation today, and I hope it helps you to understand clearly the concepts of normal and shear stress. Still, I suggest you to study by yourself additional example in the note accompanying this video. Thank you and see you in the next lectures.